Buenos días a todos. Good morning. So today we have with us Bjarne Stroustrup. As you already know, he will be becoming tomorrow Doctor Honoris Causa by University Carlos III. This is something that makes us really very happy, this opportunity, and also having him here. For those of you, I do that, but for those of you that do not know some details, Bjarne Stroustrup is a director at the technology division of Morgan Stanley in New York, and is also a professor at Columbia University. He got a master in mathematics from Aarhus University in 1975 and a PhD in computer science from Cambridge University. Actually, as you may know, Cambridge has the oldest computer science department in the world. His advisor was David Wheeler. David Wheeler was the first person getting a PhD in computer science, and he was the inventor of the subroutine. Between 1979 and 1983, at AT&T Labs, he conceived what was then called C with classes, later named C++, with a lot of influence from Simula and C languages. However, C++ soon presented a number of new ideas that made it a unique language for many domains in industry. Bjarne was head of the large-scale programming department at AT&T Labs. And this obviously is related with the unique characteristics of C++ for being able to build multi-million lines of code software products while not sacrificing performance. Since the very beginning, Bjarne saw the enormous advantages of making C++ a standard language instead of a product from a single company or from multiple companies with different dialects. He pushed for making C++ an international standard under ISO. The process started around 1990, and by 1998, we had the first ISO C++ standard, C++ 98. After a bug-fixing revision in 2003, the next major release came in 2011, which, by the way, was approved here in Madrid. And since then, every 3 years, we have had a new version, C++ 14, 17, and we are now approaching C++ 20. Bjarne participates as one more delegate in the committee. He does not take any advantage because of being the creator of the language. As for many others of us, sometimes his proposals are accepted, and sometimes they are rejected, or he is asked for more work, and he does that work. Nevertheless, you will find him in every standards meeting working very hard to make the C++ language a better language for all of you. Still, the challenge is to provide better education on C++. For the students in this room today, there are people from different companies who ask me almost every week for C++ developers for solving really very interesting problems. And unfortunately, most of the time, I cannot always provide 10 students with the required skill to be hired by them, and they complain. During his career, Professor Stroustrup has received many awards. Let me cite only some of the very recent ones that you see there, and that I call the bronze medal, the silver medal, and the gold medal, and they are. He got the John Scott Legacy Medal and Premium from Franklin Institute, the Computer Pioneer Award from IEEE Computer Society, the Charles Stark Draper Award from US National Academy of Engineering, and the Faraday Medal from the Institution of Engineering and Technology. If you don't know about those awards, I'll tell you the names of other people who got those awards: Marie Curie, Thomas Edison, Nikola Tesla, Alexander Fleming, John Backus, Maurice Wilkes, Jack Kilby, Vinton Cerf, Tim Berners-Lee, J.J. Thomson, or Ernest Rutherford. The list continues with many other awards and distinctions during his whole career. So it's for me my greatest honor and pleasure to ask all of you to give a warm welcome to Bjarne Stroustrup and let him deliver his talk.
Thank you very much, and thank you for coming. It's a bit hard to follow up on an introduction like that. But if my slides will appear, I can do it. Is there anything I have to do? As most of you saw, it did work just a minute ago. Yes, I see it. I see it's black. Let's see. Close this thing. Try again. Curse software and get on with it. So, I guess Jose Daniel gave you an executive summary of what I'm going to say, which is I'm going to tell you a little bit about what C++ is and how it came to be that way. And so basically I start out with sort of the high level, what am I trying to do? What are the fundamentals here? And then I'll give one example of source code. This is, after all, not a lecture on to teach you to write specific code. There's books about that and courses. And then I'm going to talk a little bit about the recent evolution, and then I'll get a little bit about how to use C++. Okay, it seems that I have to be over here to avoid feedback. So that's what I'm going to do. And what really matters, of course, is people. You get the most ferocious debates about individual language features. But you know, you don't really want individual language features. You want nice, smooth languages that allows you to express something that you really want. People don't really want programming languages. They want systems that are built with them. And in the discussion of programming and programming languages, I find that the application and what really matters are very often forgotten. And it's easier to get a debate about where to put a semicolon or a space than it is to get a discussion about what are you really trying to do. So from a technical point of view, I would say that stability and evolution are the key themes. You need to evolve to catch up with the world. The world changes. I'm thinking about work that goes on over decades and work that is being used over decades. You have to evolve to meet the new challenges. On the other hand, everybody wants new features and new facilities, but first of all, don't break my code. And there's an example right there. That's a marine diesel engine. It's probably the world's largest marine engine. You'll get the size here. See the engineer at cylinder head number 5? It's a big engine. If that one doesn't work, you have a very large ship adrift in the Pacific. Now, you have not seen that in the newspaper over the 10, 15 years that has been on a lot of ships on the sea. So it worked. It's good code. There's actually generic code in that one for the engine control. So when I'm talking about generic code today, this morning and the afternoon, this is not hypothetical. It is not just mathematical. Things like that. That's how you got the cars and stuff shipped in from wherever you get it from. And so stability matters, evolution matters, tool change matters. You don't write code just in a language. You use a compiler, a linker, all kinds of tools that matter. And teaching and learning. By and large, one of the things that drives me nuts is the fact you give people a really nice tool and they misuse it. So you can't just give people a tool, you have to teach them how to use that tool. I remember a long, long time ago, Arno Penzias, who's a Nobel Prize winner and was head of labs at the time, explained to people, look, why you need to learn. If you have done sawing with a saw, everybody has tried that in the old days, and you get an electric saw, what do? You do this. It hits a lump in the wood, it jumps, and if you're lucky, you don't lose a leg. And so you can't just design, you have to know what you're designing for, and then you have to teach people something about the rationale and how this is supposed to work. And so that's important. And if you look at language things, you have to build a community, because otherwise the teaching cannot go around and the knowledge cannot spread. You have to have a coherent language. That's really hard when you evolve. When you change things, it's very easy to just plug things in. I mean, you've seen cities or buildings that sort of had been put together by bad designers and bad architects and such. You know what it looks when it's wrong. I try hard not to get into that. Don't always succeed, but sometimes it does. And it has to be complete. If I give you a tool and it can do 80% of what you want beautifully, then you can write a nice academic paper about it, but it is useless as a tool. Unless it can do everything that you need in that domain. I actually don't think you should have languages that can do everything, but it is only a useful tool in a given domain if it can fill it well enough. And there's other things. But basically, being good at just one thing, which is the way you get a paper and pobble and such, is not sufficient. The saying is that a chain is no stronger than its weakest link. You have to be sufficiently good at everything. And nobody can be the best at everything. So I like to point out that I'm not claiming C++ is a perfect language. And not even that it's the best language, because I think this is a meaningless statement. C++ can be the best at something. And I've never seen anywhere where it couldn't be a little bit better if I tried harder. Okay, so purpose of the exercise here with working with languages is to build good applications. I measure the language quality in what you can do with it. And there's some applications of C++. Some of them are interesting. That's cyclotron and CERN. I have friends there, those involved in finding Higgs boson. And well, there's a guy going through high with speed limit around the Earth up there. Chat groups. I love Lego, of course. I've got kids and grandkids. It's a lot of good stuff. There's lots and lots of this. My field of study in Cambridge and such was distributed systems. Still interested in that. There's a distributed system with wheels. It's when you're into software and systems building, you look at the world slightly different from other people, at least when you have your professional hat on. But one point here is nobody masters all of these application areas. There is absolutely no one who understands all of this. As a matter of fact, as a union of all the people here, we don't understand all of those pictures. The point here being that when you build a language, you're going to get it wrong slightly. So the basic philosophy is you do what you can do well, you keep it open because you know you don't know everything, then you learn, and then you evolve it. So C++ is carefully evolved. Yes, there's a lot of design effort in there, but feedback is absolutely essential, and I've relied on it. So look, let's go back in time to the early 1980s when I was starting this kind of stuff. Ken Thompson, Dennis Ritchie had just built the first semi-portable operating system, Unix. And Linux is another incarnation of that idea. And computers looked sort of like you see them there. That machine there is a PDP 1170 known as Research. I used to work on it for a few years also. You started it by flipping switches. And it's between 100 times or 1,000 times slower and smaller than my cell phone. The world changes. So computers had less than a megabyte and less than a megahertz of power. The first version of C++, I was nervous that I would get to that limit because then it became unaffordable to ordinary people. Researchers, by and large, get the biggest machine they can get and they build the fanciest stuff. That means that the average programmer can't use it for the next 5 or 10 years. I wanted this to be used. I overshot the target, by the way. So when the PC came out, gave you a max 640 kilobytes of memory. C++ ran really nicely on it. But basically, they cost $3,000 pre-inflation. IBM PC hadn't been invented yet. And I wanted to push something which included object-oriented programming. It's not all object-oriented programming, but that was one of the buzzwords going around. Simula that I built on was known as object-based, which was what object-oriented was called before somebody picked up the name. And everybody knew it was useless. Well, this is an overstatement because 99% of programmers didn't know about it at all. But of the ones who knew it was useless. It was too slow, too special purpose, too difficult for ordinary mortals. I mean, they had to do something about this. And basically, I was talking to the geniuses at Bell Labs, and I am using the word carefully. They were geniuses. You can look them up, what they do. Basically, I was told, you want to call a function and you don't know which one it is? You should go back and do your analysis a bit better. That was a considered opinion on object-oriented programming and uses of classes with virtual functions and such. So I have this feeling that when I explain the fundamentals of C++, people say, yeah, well, we learned that in kindergarten. But it wasn't there at some point. Like my advisor, David Wheeler, invented the subroutine. How can anybody not have a subroutine, a function call? Well, somebody had to invent it, and he did. So basically, it was a Bell Labs project. I wanted to build a multiprocessor or a cluster. So I wanted to take software from the kernel, spread it around on multiple processors or computers, put in place a communications infrastructure, and run it. And if I'd done it, I had done the first Unix cluster. But I never got around to it. I got distracted. I needed close to optimal low-level programming because I needed to do the process scheduling, the memory management, the mapping to the hardware for I/O and things like that. So I needed a systems programming language that's really good at manipulating hardware. And I wanted to be able to talk about the parts. Once you have a distributed system, there's something over there that talks to something over there, and you have to be able to say what that something is and how they talk. And that's where the object-oriented programming comes from, the notion of having user-defined types. So C classes could get C, that was a really good systems programming language, and Simula, which was one of the best languages for abstraction at the time. And keep things general and flexible, because even then I knew I didn't know everything. And it's better to keep things open. And no, I never got to build it. That's an earlier vintage Bjarne there, with one of the very first graphical screens, by the way. Okay, so here's the historical view of C++, as it were. The world of computing and programming started with people writing assembler. Then there was a language called BCPL, done by Martin Richards in Cambridge. From there came C. There's Dennis Ritchie there. If you've heard C versus C++ wars, I'd like to point out I had lunch with him most days for 16 years, and we never had a harsh word. It's, I mean, if you are a languages fanatic, there's something you have misunderstood. The purpose of the exercise is to get good systems built. Dennis used to say in public, there are languages designed to prove a point, and there's languages designed to solve a problem. There's no doubt which line we're in. By the way, the assembler here, this is David Wheeler, that was Daniel mentioned, and that is my advisor. He invented the subroutine, as it were, and it's one of the about 10 people who claim to have built the first compiler. But here, at this line, the problem to be solved very often is how to optimally use the hardware. You look to the hardware, you use the hardware, you want every cycle, every byte, because you tend to be implementing something that needs that. It could be the operating system, it could be a compiler, it could be a simulator. Basically, you saturate the machine sooner or later. And this is what that line is about. Then somebody, there's Bacchus, figured out that actually we should move away from the hardware. We should actually have something that's fit for humans. So he designed Fortran formula translation, where you basically takes the formula, a language that is suitable for certain humans, very weird humans, engineers, scientists, unusual species, but those, and built a language, and then had the computer itself translated into the hardware here, to their assembly code. So that was the first sort of high-level language, and I still think that was the biggest improvement we've ever seen in programming and programming languages. It's the first time somebody lifted their eyes from the hardware to the humans. And as soon as the engineers and scientists got something, everybody wanted one too, right? So the business people got COBOL, the string manipulators got Snowball and such. We soon had total chaos. About 200 languages, and the people couldn't talk to each other. They had different languages, different data formats, different ways of thinking and such. And here comes then Christian Nygaard, who together with Ole Johan Dahl had the idea for Simula, which is basically don't give people domain-specific abstractions. I mean, here you get matrices, here you get records for business and manipulation of records. How can you do both? And says, give people the facility to build their own types. If in Simula you want a matrix for linear algebra, you build one out of the tools given to you. And if you want the record manipulation for COBOL, you just build it yourself, or you have a library for doing it. So that's a great idea, and I needed to be able to do hardware, I needed to be able to do abstraction, so I put those two together, and lots of things came from there. Remember, before there, everybody knew it wouldn't scale and it couldn't be used in this kind of field. Okay, and I've been working on this for a while since. When I first made this slide, it fitted. Now it doesn't fit anymore, so you get this little strange thing. And C++'s role, as far as I can see, is to write elegant and efficient programs. I hate choosing between those two. So both of those, and you do that by defining and using lightweight abstraction. So for linear algebra, I get myself some matrices, some triangular matrices, some band diagonal matrices, da-da-da-da-da-da. That is, I don't build the matrix in, because everybody who has tried that has built in the wrong matrix relative to some domain. And if I'm in telecom, which I were, you build dial buffers and things like that nobody else has thought of. And it focuses on resource-constrained applications. If you are on a small machine like a watch, you have severe computational and power constraints. And actually, quite amazingly, if you are on a server farm with a few 100,000 processors, you again have power constraints, memory constraints, and you fill them up. So if you have a language that's, say, twice as slow, you need 2 centers. They cost $60 million and $10–20 million a year to run. So you don't want things to be twice as slow if you're thinking about this. There's a lot of things these days that are 8 times or 50 times slower. Anyway, so it offers a direct map to hardware, 0 overhead abstraction. This is C++ in 2 lines. And no language is perfect for everything and everybody. I mentioned that. I should mention it again. So I don't know if you've seen the Dragon book. This is Alejo's and others' book on how to write compilers, which is basically about how to defeat the dragon of complexity using the tools of computer science. Sometimes the dragon wins. By the way, Al is another good friend. I had dinner with him last week, actually, and Brian Kernighan, both, another C guy. The Bell Labs was a great place, nowhere else like it on Earth. So the map to hardware, as I've mentioned, it's your operations map to machine instructions. It doesn't map to lambda calculus, and then you have to figure out how to get to the hardware. The memory is just a sequence of objects. I mean, look at the memory, look at what the hardware does, that's what it is. And this is the abstraction that Dennis Ritchie put in place. And you can create objects by simple composition. You stick objects of the same time next to each other, and you've got an array or whatever you want to call it, and you stick different things together, and you get classes and structures, and you use the pointers to get to values when you have to think that moves or grows in size and things like that. This is really simple. It's one slide. There's nothing really clever here except the simplicity. And this is actually an abstraction, but usually it looks like just the way the machine is. But that is really simple. That's the key to C and C++'s success, and that is something that most languages have not copied because there are problems at this level. This is hardware. It's down there, close to the hardware, close to the machine. It's quite unpleasant down there when you want to use it really well. And so you have to abstract away from that. You have to get from the bits and the bytes and the low-level stuff. And so you do with building abstraction mechanisms. You build classes, class hierarchies, templates that are parameterized classes, parameterized functions like that. But most of the time when people have done that, they've said, well, to do that you have to pay for it. And quite often they give you good abstractions and they'll take away 90% of your computer to give you that, or even 99%. Just look at the overheads in various languages, which is fine if you don't need to use the hardware really well. But if you are in writing things like operating systems or space probes or server farms or the communication software in your cell phone, you can't just afford to throw that away. So one of the principles I concocted for C++ was what you don't use, you don't pay for. That is, the argument that, yeah, you'll need it sooner or later, so you'll pay for it everywhere. I just didn't believe in. I'd heard that one too often, and quite often it just bloats. And if you do that in many, many areas, you will end up getting something that just is too complicated and costly. And what you do use, you shouldn't hand code any better. So if I produce a facility for providing a class or a generic type, I shouldn't be able to go and hand code it any better. Preferably, I shouldn't even be able to write assembly code that runs any better. And sometimes we succeed. So examples are little types that we used all the time. Complex numbers, points, dates, tuples. No memory overhead, no indirect function calls unless you want them, of course. No reason to put things in dynamic memory unless you want to, of course. And we're really good at inlining. That is, if you can compute something at compile time, rather than execute it at runtime, you usually win and you get a smaller program that runs faster. If you're running on certain hardwares on a certain constraint, this makes sense. If you are not, do something else. You can use more general things. And so basically abstraction can simplify your understanding. It can simplify the use of facilities. It can also simplify abstraction because as you optimization, because as you abstract, you're getting closer and closer to saying what you want as opposed to how you want it done. And that gives freedom to optimizers that sometimes can do a superb job. Of course, you have to know what you're doing. And notice that even your hardware is an abstraction. There are no processors that actually execute x86 instructions. What they have is a layer of silicon that takes 886 instruction set, which is awful, and translate it into something that looks more like a MIPS instruction set, a wide instruction set, that can be optimized and executed better. So your hardware is an abstraction. The memory model I showed you there is an abstraction, and you know your libraries provide other abstractions. If you think you have a matrix and can do matrix multiplication, it's an abstraction that maps into sequences of objects, that maps into the instructions, that maps into the other instructions, go all the way. It's abstractions all the way down. Turtles all the way down, if you know that universe. Basically, don't make abstraction an excuse for being sloppy. Always abstract from concrete examples. You have to know something before you can abstract for it. Usually you need two uses, you need two ways of doing things before you can make an effective abstraction. I'm not saying this is easy, but you have to be careful and then you can do it. So the basic mechanism in C++ for starting things is a class. It's a user-defined type. The reason it's called class is that Christian Nygaard and Ole Johan Dahl were not computer scientists because, well, that hadn't been invented yet. They were actually mathematicians, and they knew about classes and sets and things like that. They didn't think in terms of types. So it was called class. And if you used any language that uses the word class instead of type, you can say thank to Christian Nygaard, because that's where it comes from. But anyway, there's two parts usually. There's a public part, which is the interface, and the private part, which is the representation and the implementation details. And so the simplest thing here is there's something called a constructor that says, how do you make one of these? How do you make a vector? And a destructor that says, how do you clean up the mess off when you're finished? So if you go down and use it here, I want a vector of doubles. Oh dear, I made it a template because I wanted a vector of any type I could think of, and so parameterized with an element type. So I want a vector of doubles, and I initialize it with a well-known set of constants. And if instead I want a vector of string, I do a well-known set of language designers. And basically, in both cases, it calls that function that takes an initializer lists and does what is needed, which is to grab the memory here where you can stuff the elements, put the elements in there, and we're off and running. And then there's some access that says, how do you access a vector? There will be the subscript operator and things like that. And when we're finished, we have to clean up this. We have to give these elements back. So at the simplest level, it gives back some memory. But notice that strings in C++ are themselves a handle with some elements. So this has to work recursively. So this one built recursively a two-level structure, one that is a vector of strings, and the strings that are a sequence of characters. You get a little tree. And when you come to here, well, it cleans it whole up. It walks that data structure and clean it up. This is very general. In particular, if you look at the C++ standard library, vectors, lists, singly linked lists, maps, hash tables, sets, multisets, strings, they're all like this. It's basically that previous slide, you can now build all of those. There's a few other tricks that has to be to it, but the fundamentals were right there. Other things, I like that they're a handle, and then there's a value that controls it. Threads, I mean, it's just a little handle that allows you to talk to something that manipulate the register sets of a machine. Talks to the operating system often. Lock guards, you keep track of which locks you've got. And file streams, it opens a file, it sets aside buffers for using it, and all of that. And at the end, It cleans up the mess in all of those cases. It's constructors, destructors. This is known by the brilliant term RAII. Resource acquisition is initialization, which is the best example of why I should not be in marketing. You get this idea, and you name it something like that. Clearly, I was not thinking about selling this stuff. Anyway, but the point is that this means that garbage collection is neither sufficient nor ideal, because it's not sufficient because it can't clean up the messes. We're really good at acquiring things. We're really bad at remembering to give it back. Try your public library as an example. But it's again and again that. And it's not ideal because a garbage collector collects garbage when it feels like it. So it builds up a lot of garbage and then it has to clean up the mess later. I don't just want everything cleaned up. I want it cleaned up as soon as possible, because if your objects live for twice as long, you need twice as big a computer. Because all of these unused objects are lying around waiting for the garbage collector to wake up. I want to clean them immediately. That's where all the magic happens, right at the end of the scope. We had a competition once for the favorite C++ feature, and a guy called Roger Orr just sent in one character, that one. That's where all the magic happens. If you understand that one, you understand C++. So let's see some code here. Here's some code that I unfortunately see a lot. You take a new gadget. New is the operator that creates an object, and you assign it to a pointer. And since I acquired something over on the free store, I have to give it back. That's what delete does. It reverses its thing, and this calls the destructor, and they do cleanup. Okay, there's a long way from here to there, and people forget that one, and you have bugs. And they scream for a garbage collector, but remember, you don't know what's inside the gadget. It might have a lock, it might have a file handle, all kinds of things like that. I have a socket open something. Furthermore, if I throw an exception here, or if I return, I may never get to there. So this is asking for trouble, and unfortunately people do ask a lot of trouble because there have been other languages where there's a garbage collector and they're used to having to say new to get something. So how do we solve this? Basically, we have something called shared pointers in C++ since C++ 11. Before that, we had other things, so it's not particularly new. But basically, it says, make me a gadget initialized with n, whatever it is. Since I'm not telling you what gadget is, I can't tell you what the initializer list is either. But anyway, we just use the number n. And it says, make me that, make a shared pointer to it, which is a counted pointer, and put it over here. So we get to here, and you get out of here, and it sees if there's anybody else that's holding on to this object. If there isn't, it just deletes it. Similar with return, and now I can't forget to write the delete, because the shared pointer keeps track, and if there's no other uses of it, it gets destroyed. So this is a form of garbage collection that actually works, because it correctly releases resources at the first possible moment. That's good. On the other hand, I don't like garbage. And I didn't share this object with anybody, so why should I do use counting? I mean, what's going on here is the use count goes from 0 to 1, and then it goes from 1 to 0 at some point. This is waste. This is bad waste. So we have whoops. Slide missing, sorry. So we actually have a version of this that is called make unique, that makes a unique pointer. It doesn't have a use count, so it doesn't have extra work to manipulate a use count. And people say, what's wrong with the use count? Well, it doubles the size of the pointer, because you have to know where the use count is, and you have to update the use count. But in a multi-threaded system, updating a use count that could be shared means that you have to synchronize on it. And synchronization is one of the things that slows you down significantly. So changing this slide to make unique would significantly speed up the program. One of the things you can do is to look at your code. If you have a lot of shared pointers, see if they should be unique. It usually speeds up the code. And anyway, the other thing is, why am I doing pointers here? If I'm not sharing it with anybody, this is the way it should do. I want a gadget. I want it initialized. If it throws there, of course the destructor fires. If it throws there, if it returns there, the destructor fires. If I fall out the bottom, the destructor fires. So I have simplified the code radically. I've made it run faster. Ta-da! This is the idea in improving a language, improving design. You want things to be shorter, simpler, and faster. Of course, we don't get this lucky every time, but when it does, I'm very happy. So this is a good example. There's only one problem left. If all of your objects sort of look like that, they're local variables. But we can't do everything with local variables, right? I make something and I want to give it to somebody. And that's one of the reasons people have used pointers, because they don't want actually to move something, to copy something expensive over there. They take a pointer and put the pointer over, and now he can use it too, and I can use it too, and we can get a race condition on it in a distributed in a concurrent system. So we have to do better, and this is the move idea. So we don't actually want to copy, we want to move. Look here. There's an object here in my hand. Now it's over in this hand. I mean, who would make a copy over here and then destroy the original? Well, computer scientists, that's who. And on the other hand, we knew how to do this when we were about 4 to 6 months, right? Persistence of objects. Asked for the people in sort of child psychology. I mean, it didn't disappear and a new one come around. It just moved around, right? We can do that. That's fairly easy. So we have the gadget, and we want to return it, and we want to move the gadget out. And if we can figure out how to move, we can do that. But notice that gadgets tend to be, this is my sort of generalized type. A gadget tends to something that has a handle to the real stuff. That's what a thread is, that's what a file handle is, that's what a vector is, that's what a string is. So all we need to do is to look at that pointer and copy it somewhere, and then null it out there so this one's destructor doesn't do anything. Then we have moved it. So we have implicitly used the pointers inside an abstraction. So what we're doing here, we're building from the hardware. The simple abstraction is a pointer, and we get to the next level where it's a gadget, which is any other type that looks like that, and we can now move it out. So basically, there's a quote to Roger Orr, and the key to C++. We started very early on in 79. Classes, member functions, public-private function declarations, in particular the member functions, constructors and destructors. All of this stuff was in place by Christmas 79. This is not new, except for move. Move is new. Okay, but that's the key to all of this stuff. Now, there's been a lot of people saying C++ is an object-oriented programming language. I didn't do that. I didn't say that. I said C++ supports object-oriented programming, and it's actually pretty good at it, especially if you're under resource and time constraints. But it doesn't try and insist you do things that are object-oriented for any definition of object-oriented. But it's good technique for some areas. And one particular thing is I want the direct map, and I want value semantics. So A becomes B really implies that A is equal to B, and if I modify A, it doesn't affect B. That's sort of what most people would think, unless they had had a serious training in Java or something like that. where they can't quite, it looks as if I made an assignment like I did an integer. But if it was a matrix, suddenly there's a sharing going on. And I'm very worried about sharing, partly because of concurrency, and partly because if I'm sharing with somebody, I don't know what they're doing with it. And so I have to know, if I'm somehow sharing with him, I have to know what he's doing. And when I'm writing code, we want separation of concerns, separation of code, and so I don't want to have to know what he's doing, even if I can assume he's doing something great. So here, there's an implied sharing in some languages, but not in C++, unless you have programmed it to do it, which is fine. You can do anything, and sometimes you want to. The other thing is I like the separation of function and data. I mean, square root of 2, I understand that. Having to express this object-oriented so that it's I apply the square root method to the object with the value 2 is not the way I think about it. I have a math training, and I think I know what square root of 2 is, and that's what I want to say. It's we have 300 years of experience. Similarly, A plus B, it's an operation on A on B. It is not an operation on A given an argument B. If it was, what would B plus A be? The same or something different? I really want that to be defined, and I want to sort the vector as opposed to anything more clever and complicated. Okay, so C++ became a bit of a success, and one day a couple of people came to my office at Bell Labs representing IBM and Sun, and explained to me that I wanted C++ to be standardized by ISO. And I said, no, it's not ready, it's not finished, it's still experimental. They said, no, Bjarne, you got it wrong. Large companies and large projects cannot rely on a language that is controlled by a single organization, like AT&T. We, of course, trust you, but you might get run over by a truck. This discussion took about 2 hours, and they did use that. It wasn't a truck, it was a bus, but they did use that example. And so I agreed to standardization. It was considered a necessary evil, a lot of extra work, a lot of bureaucracy, but the only way that the world at large could depend on the language as opposed to just one organization that might optimize it and tweak it to their own benefits. And it was understood that there was no alternative to that. Of course, if you have enough advertising dollars, people have proven that you can actually do it, but I didn't have any advertising dollars. So there's many kinds of standardization. We picked the gold standard of standards, which is ISO, and long-term stability is what we aim for. You can't just change the language because you get a new customer or something like that. It's more bureaucratic, but it gives stability. It's vendor neutral. It's important for major users. If Google doesn't like it, they'll try and change it, but they'll get into a fight with, say, Microsoft or Bloomberg or Intel. That is, you have to have a balance between different users from different industries and such. That's good. Unfortunately, that deprives C++ of development funds because people are willing to spend a lot of money if they can get a differential advantage. That is, an advantage over those guys that are the enemy. If you, for 1/10 of the cost, could build something that would be just as good, but the guys over there could also use it, the money doesn't come. I've found that again and again. So I guess the point I'm making here is that language design is not just about language. It has to do with sociology and business concerns, and a lot of things has to do with people and the way people go about their lives. Since '89 or so, the language has been in the hands of the Standards Committee. So we started there in '90, and the world was still black and white. They hadn't invented color yet. And it was a small group there. It wasn't easy, but they were at least small. Here we are actually in Madrid celebrating that we finally got C++ 11 after 12 years of work or something like that. There's a reason we're happy. I'm sure Jose Daniel is there also. Yep, there. And I was there too somewhere. And so in 14 the group has grown, and in 17 the group has grown, and it keeps growing. At the last meeting we had 181 people present. How do you get 181 people to agree on something of importance? I mean, a lot of these, their mortgage and their future and pension and company and such depends on this. They can get very emotional about this. Furthermore, a lot of people are really, really interested in languages and systems, and they can get very emotional about this. Oh yes, of course, the committee, that's half of it. The other half is there via email and IM and such. You have to be there to vote, but you can still argue on it. So it's sort of interesting. The next meeting is next month. We're going to freeze C++ 20, and it's going to be interesting. Standards meetings take 6 days. We start usually over breakfast, 7:30, carries on, formal meetings in the morning, formal meetings in the afternoon, formal meetings in the evening, and about midnight you go to sleep. And then we do that in nice places so people think we don't work. Yeah. Anyway, so let's look at the evolution of C++ sort of from a time scale. We got 98, got the first standard. That was a solid workhorse. We got exceptions, templates, and all the stuff that came from the earlier days, like virtual functions and stuff. Templates is the basis of generic programming, where you can parameterize a type or a function with another type. And so the major improvements in 11 after 13 years of work. We got many more libraries. We got concurrency supported in a type-safe manner, random numbers, regular expressions, lambdas, generalized constant expression, da-da-da-da. This is not a language detail talk, so I'm not going to go there. You can read up on it if you like. I do recommend a book called Tour of C++. You can get the second edition now. It gives you a view of modern C++ and has the great virtue of being this thick, about 240 pages. And it covers all of C++ and all of the standard library. So if you have an older view of it, that's the way you upgrade. Of course, not in total detail. So C++ 14, complete C++ 11. There's a point here. When you design a big project, there has to be a feature freeze. And the feature freeze for a language, which is a huge project involving many nations and many corporations and many individuals, you have a feature freeze about a year and a half before the standard. Now, in this period of time, we will notice that something is wrong. Furthermore, there will be great ideas that we just didn't manage to get in before the feature freeze. One of the reasons it took so long in the beginning was people kept pushing because it was so important to get something in that we got postponement. We decided never again. We have a 3-year cycle and we are keeping to it. Anyway, so we got all these features. And so after a while, when the standard's in place and we can try things in combination that we couldn't do before, we learn a lot of little things. So that's a completion. It's a polishing thing. No radically new thing, no new programming techniques, but just basically completing the work of the major change. 17 was supposed to be a major expansion and improvement. It wasn't really. It's unfortunate. The committee was getting conservative and wouldn't take chances. They were willing to do lots of little things and no big things. I'm sad about that. C++ 20 could become great because the things that should have been 17 that we couldn't get ready will come. Concepts, modules, contract, coroutines, things like that. I will explain what that is next. But the point is that we were trying for a major release, minor, fixing up problems, major release. Major means changing the way you think about code, changing the way you write code. Minor means fixing the little details. Okay, and again, this is not science fiction. We have 3 major vendors, implementers, and many more that I don't fit on the slide. It's shipping. People are using C++ 17 today in production worldwide, and some of the features of C++ 20 is already in use at a very large scale. Okay, I love science fiction, but not when I'm doing a technical talk. So C++ 11, lots of features that lots of you today know about. Finally, we got type-safe threads and lock kind of programming. Threads and lock kind of concurrent programming is the worst there is, but it's the foundation of everything else. So we had to get it type-safe. If you like void stars, you don't like this stuff. If you want to just refer to it as what it is, this is great. Lambdas that can be seen as local functions. It's basically a syntax for giving you a function object so that you can pass them around with data and operations. Good stuff. Lots and lots of stuff here. I'm not going to go into these details. I'm just going to show you one example. So here, I'm going to do a find all. So I want to find all the elements in C that has the value v. And it is parameterized. C is some kind of type, and it's better be some kind of container. And the v is of a type. And basically, I want to return pointers to the elements in C. This is a little bit primitive, but this is C++ 11. And a couple of slides further on, I'll show you how to get that less mysterious. So basically, the first thing I do is I get myself a container, a vector of pointers to elements. Value type is what we call the element, what we call the name for the element type in a container in the standard C++ library. And then say, for all x in C, if x equals v, push its pointer at the end of the vector. So this vector keeps growing, and we can return the result. And this will work for vectors, it'll work for lists, it'll work for container you invent tomorrow if you follow the conventions of how you name things. That's pretty good. And now let's test this. I have a container of characters known as a string, and I'll have Mary had a little lamb. And let me find all the a's in M. In other words, I want to set up a vector of pointers coming back, pointing to that, 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 and that. And if you go around, that'll do it. It'll start with an empty vector here, and when it finds that A, it sticks a pointer in when it finds that. So, fairly simple, right? And then I'll do a simple test. I will go for all the pointers that are coming back here. I will test if they really point to an A. It's a test program. So, this works. And the important things are what is not on this slide. I do not know how big this vector is going to be. I could fire this find all up on a megabyte of data and get back 1 million pointers. So in C++ 98 and some other languages, this will be a serious performance bug because it'll try to copy 1 million pointers. But we have move semantics. Vector uses the move semantics, so it simply takes the descriptor, the vector descriptor, which is usually 3 pointers, move it to the other place, zero out the first one, and we have moved the 1 million of pointers out of the function find all out to here. No overhead really. 3 word assignments. So there's no allocations here. You don't see any allocations. They're all hidden, abstracted away. And you don't see any pointers here except I asked for pointers, so I got them. because pointers are really good at pointing to things. And what I asked for was, where are the things in the constrainer? So obviously I need pointers for that. But I don't need pointers to get things out of the function. And there's no allocation. I don't have to decide how many results I'm willing to take. I just take one and let it grow. If I run out of memory on my machine, this program will terminate with an error. But in most cases, it'll just run. It'll grow to the size it's needed. And by the way, somewhere down here, I left out the curlies around this. Somewhere out here, this all will be cleaned up. So there's no allocations, no pointers except for what pointers are good at, no pre-allocations, no nothing. So this is the improvement here, is the stuff that you don't see, and it runs blindingly fast. Okay, C++ 14, basic cleaning up a lot of stuff. In particular, we introduced in C++ 11 something called const_exp, which is basically a facility for saying that if you can execute this as compile time, do. This allows you to, at compile time, do type-safe, type-rich programming, something that Gabby Dos and I got into C++ 11, and everybody knew it was unimplementable and useless. And by 14, they were getting very enthusiastic, and they wanted restrictions removed to make it more general. We have learned that it was useful. For 17, there's more restrictions removed, and it's all over the place. For 20, I mean, it's all over the world. So it sort of grows based on experience, feedback. Okay, that was the example here. Brings type-rich programming to compile time. And so here's an example. It's a request I had from somebody in the Japanese embedded systems industry. They wanted to calculate integer square roots at compile times so that they wouldn't have to do it off on the side and then copy it in and get it wrong and things like that. So we wrote one. That's the simplest algorithm I know for integer square root. Just keep doubling till you get too far, and then you know where you were. And now I can say, give me the integer square root of 9, that's 3. I might get that right, but there would be a magic constant in the code if I just build in 3. Now I want the integer square root of 1, 2, 3, 4. There's a good chance I'll get it right on a doodle pad, but it'll be less reliable and I couldn't see what it was. So here just calculate it at compile time. And we can actually do it. One of the principles of C++ is that if I can do it with an integer or some other built-in types, I should be able to build my own type that works just as elegantly. So we don't actually just want integer calculations at compile time. We want to use types. So let's see here. I want the weekday of June 21st, 2016, and write it out. That's fine. This is actually a real library. It's coming into C++ 20. It's the handle time zones and other good stuff. Go back into time. If you want to know which is the first Sunday in 1942, it'll tell you it. So you can do this, but more fun. In C++ 11, we got static asserts, which is basically saying calculate this at compile time, and if it's untrue, give a compile time error. So this one says, if the weekday of June the 21st, 2016 is not a Tuesday, give a compile time error. This is very powerful. This also, by the way, proves that there was no calculation done at compile time right there. That has been calculated before I even started the program. So the embedded systems guys really love it. The performance guys really love it because there's very few things that are as fast as just loading the answer. Good stuff. Expression of ideas. I like to express things directly. There was a for loop I showed you. For all x in V, auto says, well, I know what the type of elements in V is, so if you want to talk to them, I don't have to repeat myself. I mean, the compiler knows what the elements of V are, and so I don't have to tell it. And this is quite useful. It can be overused, and it is overused. Every new good feature gets overused and misused. It's unavoidable. people get over-enthusiastic. But anyway, so here is a loop saying, give me all the elements in order and figure out what type it is. I don't want to know. I can try sort V and do this as the comparison element, comparison function. That's lambda here. So it takes x and y and see which one is bigger, give you true and false. That's by the way you sort in the descending order instead of the default ascending order. And this is very useful for algorithms, and it's very useful for various forms of interaction, GUIs and networking and such. You set up a callback, that is, I say get the sort of callback and give an operation that's going to be when it fires. And you can specify context of what you're going to do, good kind of stuff. You don't have to use all of this everywhere, but we're slowly improving the expressibility of the language under the constraints of the zero overhead principle. If you can hand code this any better, we need to fix this. We have 10 years of experience that says you can't. Okay, let's go on. So, as I pointed out, stability is a key feature. You can't remove a feature. Just about everybody says C++ is too complicated. Of course it is. I mean, we have 40 years of experience, and there's a lot of stuff we can do better now than we could in the old days, but the features from the old days have been used by millions of people over the last few decades. So people say, make it simpler and give me these 2 extra features. I used to do some experiments, give a talk like this, and afterwards I give people a piece of paper, and I say, please, would you each write your 2 favorite extensions that you want on the paper and give them to me. And what I found was for n people, I get roughly n unique examples, requests. That is, they don't actually agree on what they want. So it's easy, and they don't want me to break the code. The way you solve this conundrum is actually to simplify doing simple things and leaving complex things in place, leaving old things in place. So make simple things simple under the constraint of the zero overhead principle. And so we can't actually simplify the language, but we can simplify uses of the language. And as ever, I'm more interested in how you can use the language well, more than what does it really look like in a theoretical paper. And so the example here, this is way we wrote calls in the old days. We can then do this. Then we can start using algorithms that go for each. And these days, we can then say for each, call f for every element in V, and give the library permission to try and optimize it using vectorization and threading if needed. So here we're actually doing something that is far more advanced like there. It is almost as short, and actually it is shorter, and we're making progress, despite the fact that people want simpler things and additions. And C++ 17, a little bit for everybody. I've never met anybody that didn't find one of these things for helping them. And I would say most people think there's too many little features. That's certainly my opinion. 17 should have been something more significant. The important thing, I think, is a parallelism library. The fact that we can now say sort and allow people to parallelize, and we can have quite a few algorithms where vectorization is important, and that is in the standard coming in. The implementations are only coming now, but I expect they will get better and better over the years. And we have variant optional and string view, a few other things in the standard library that helps. So where do we go from here? I would like to do something major, and well, you actually need some philosophy. I would like complete type and resource safety. I want to go as fast and faster than anything else. I want to be able to use modern hardware and significantly faster compile time while I'm doing it. This is not a little dream. This is it. And the best is the enemy of the good. There's always people saying, well, we can't do this now because next year we'll have something better. Yeah, right. But the point about evolution is to somehow know roughly in which direction you're going so that you can do something instead of just being paralyzed by the set of alternatives. So I want to make C++ a better tool for demanding applications. Oh yeah, 2 philosophers and an engineer. Yes, I think I explained that. Basically, we need a philosophy, a guiding philosophy for how you go forward. You can't just add features because then you are not going in any particular direction. Every feature carries a cost for teachers, for manual writers, for implementers. Without a philosophy, language design becomes mere hacking. And so we try hard. As a matter of fact, I realized that a long time ago. There's a book called The Design and Evolution of C++, which I wrote in '94, which documented some design rules I had made back in the 80s when I realized you couldn't just look at a language feature and then see if you liked it or not. You had to have some design rules. They say, does it meet my criteria for getting in there? Does it actually help in the big picture? So I wrote that. And by the way, there it is. Well, also the Japanese version. That's the way it looks. It just got reissued. It is now available again after having been out of print for 10 or 15 years, which is, I think, interesting. There's some kind of renaissance going on in C++. So basically, you set the criteria, and here's an example. Lots of examples, and you have many more rules, but let's say I like strong typing, static typing if I can. I don't like the preprocessor. I'm still trying to get complete type safety, and I'm trying to get rid of macros. It's really hard. People are addicted to the bad code they are writing. So what do we want? Major release for 20. And we're going to get concepts. I'm going to show what that is. They're shipping. Contracts, modules. Contracts is what I'm doing a lot with Jose Daniel. Modules is what's going to give you compilation times that are 5-10 times faster than now. Times, not percent. This is major. Coroutines, I'd like to do coroutines. Let's look at this. I want to support generic programming. And if you go back in my first papers, you'll see that I used macros and conjecture that was good enough to do things like parameterize a vector with an element type. I was wrong. I had the right problem, but that didn't scale. So in '87, I had some principles, as usual, trying to build criteria and principles and then do the language features to fit them. I wanted extreme generality because I don't want just what I can imagine. Zero overhead, this is C++, and I want well-specified interfaces. I mean, I was the one who designed function argument checking that you see in C today. You can say square root of 2 and it'll actually work. It didn't in C in the old days because 2 is not a double and you crash. So anyway, I was the one who did that. So I wanted well-specified interfaces. I got the 2 first one. Nobody knew how to do all 3. Not I, nor anybody else I've talked to. So 2 out of 3 is not bad, but it's not really good. It's given me trouble forever after. The problem with generic programming is that templates, the mechanism for expressing generic code, provides compile time duck typing. Duck typing, if it walks like a duck and it quacks, it's a duck. Well, in in a program, that works most of the time, and sometimes you find it was a rubber ducky and your program crashes. So you have to do better. And templates, even under those uncertain problems, they were flexible, performance was great, you could do interesting meta-programming, you could do compile time computation. Yeah, you got write-only kind of code, and you got appalling error messages. I mean, I assume most of you have seen those error messages. You make a tiny little error and you get 50 pages of error messages. It's not very helpful. The solution is, first of all, you generalize expressions. If I want a value, I should call a function. I should not do something messing with class templates. I mean, we have, as I said, 300 years of experience for writing math. That's what I want. If I want a generic square root that can handle complex and other things, it should be called square root of z or something like that, the parameter. It'll fix the right thing. So first of all, we take all the clever stuff out, just make them into functions that looks like anything else. And when we want precisely specified concepts, if I try to take a square root of a duck, I want to be told immediately that I'm a square root and I want numbers, not ducks or whatever it is. So anyway, that's what we can get. We're going to get it. Basically, how would you like to sort a vector? In C++ 20, this would be anything that's sortable, and they insisted on auto to make sure that you didn't think it was an ordinary function. I don't understand why you want to know that, but basically you want to take something that's sortable and sort it. And if you want something that's a list but not sortable, lists are not sortable in C++ because the criteria defined in the standard library is that you are sortable if you have a beginner and end, if you have random access, and you have element type with a less than. Lists don't have that because you don't have random access, so you can go in, take a list, copy the sequence into a vector, sort it, and copy it back out again. I'm here using a library called the ranges that's in C++ 20, so you can actually write that. That's I think, the best way of sorting a list in modern C++. And so a vector, it sorts, it uses that function, whatever it is, sort the list. It notices that it's actually lists aren't sortable, but you can use the list thing and it'll do it. And notice that we don't have to say that sortables are better than lists, because the compiler knows. The difference between a list here and a sortable is that a sortable has random access. So if you have random access, it gives you the sortable. If you don't, it tries out the list. It's quite good at figuring that out. We compute it. And so how do we define these concepts? I told you what sortable was. And the only thing is that you can read the manual, you can read the standard to see that. But the compiler does not read standards or manuals. So you have to be able to say it in a way a compiler can understand, and that's the way to do it. If you have a type T, it is sortable if it is a sequence, and if it has random access, and if its value type is ordered. Poof. That's shorter than you could say it in English, and more precise. So that's good stuff. And what is a sequence? It's something that has a begin that gives an iterator, has an end that gives an iterator, and that iterator type is an input iterator. So that's another concept which you find somewhere else. But here you've got the basic framework of defining what means to be sortable. And it's on one slide. So this is simple. I have endless trouble with people trying to make it more complicated, but that's what we'll have to do. And so this is in. This is voted in. This will be in C++ 20. That's not the trouble we're going to have in Kona next month. This is the trouble we're going to have in Kona. Contracts. We thought we had it. Joint work with let's see, with Bloomberg and Microsoft and Facebook and Jose Daniel and me, roughly, and others. Basically, we want to be able to do facility for specifying contracts. These are preconditions, postconditions, and general asserts. And so basically, I can say, when I push a queue, it mustn't be full, and when it's finished, it mustn't be empty. It's very classical stuff. And if I want to do something, I can write an assert that tests any property in it. And if you thought that was simple, you haven't seen the 300 messages we had a discussion over the last 2 weeks about how to do that. Maybe. we should get it, but no man's life, liberty, or programming language is safe while the committee is in session. So apologies to Mark Twain. Okay, contracts. Yeah, there's different levels of contracts. There's the basic ones that you can put in place, and there's expensive ones, which we call audits, that you can do really complicated things for debugging. Like here, what have we got here? Binary search. And it really only works for sorted sequences. So to test whether it is a sorted sequence, you have to use an ON algorithm, whereas the purpose of using a binary search is to get an O log n algorithm. So you can't do this all the time, but you can do it for testing. So we have different levels of contracts. Now this is the biggie. Personally, I like concepts an awful lot, but this is probably the feature that if we get it, notice likely or probably, it is going to make a big difference. Clang, people from Google at Clang reports 2 to 4 times improvements in compile times in their heavily optimized large parallel builds. Microsoft, who has been working on it for a bit longer, reports sort of 5 to 50 times improvements. So if you think about 7 is sort of the ultimate random number. That is what I think about. I'll probably get 5 at least, but I would like 7 or 10 times. I mean, if you've got a server farm with 100 computers, you can retire most of them in a year or two. This is good, important stuff. So basically, I want to import I/O streams. Instead of including it and having to compile all the text, I can import a semi-compiled version of it. And then I can I'm defining a module called map printer, and I want to export something here. That's it takes a sequence and it prints a map, and I require that it is printable, both the key type and the value type. So I'm using the concepts here, and then I say for each element in that map, I want to see its key value pair and write them out. So this is pretty good stuff. This stuff here is C++ 17. That's structured binding. It allows me to break out data structures as I use them, instead of first assigning the key to some key value and value to some local value and then go and do it. I can just break them out in one sentence. This checks that this all works, and it exports this particular template. So if you now want to use it, you say import map printer, and you've got it. And the point here is you get better code hygiene, and with better code hygiene, you get it to compile faster, because you don't have to do it again and again and again each time you include something. And when you actually import it, well, there's less of it to import because it's been compiled already. We're not back in the token soup and the character soup that we were doing before. Then, the question that I've been asking myself and others have been asking is, how would you like your code to look like in 5 years? And a lot of what's driving my work is that I try to imagine what I would like it to look. And you can get things like this. This is not C, it's something else. And it's much simpler, much safer, and faster, by the way. So I asked this question, but the standard will only tell you what's legal. It'll not tell you what's good. So we have to work on something that's a set of rules that can help people pick the good parts of the language and avoid some of the old mistakes. And if you think your code in 5 years should look much like today, that's not a very ambitious answer. It's probably the wrong answer. It may be that a lot of your code will look like today, because it is today's code and you haven't got a chance to fix it. But we have to have an idea where we would like to be. So that's it. And so we attack the problems of what is good code with a sort of a drug cocktail. You know, there's illnesses that if you give them just about any drug, they evolve the way out of the poison. If you give it 2, it's harder to evolve out of the problem. And if you give them 3, they die. That's the basic idea of what we're doing here. The problems with writing code are well known, the fundamental ones. They've been around for 40 years. We have experience with them, and they don't scale. If you want garbage collection, it solves some problems. If you want static analysis, fully static type checking, that solves some problems. If you want dynamic checking, it solves some problems, but none of them solves most problems under the constraints of the zero overhead principle, which is where I want to go. Because one of the things I want is small, guaranteed correct programs that run fast. And so I'm going to do that. I'm going to do that. We improve the language, we get some general coding rules, we give some library support, and then we fire up a static analyzer. This is sort of my attempt. You saw the dragon from the dragon book. This is a modern version of that idea. You give people a set of tools that allow them to solve the problem. And target type and resource safety, get rid of overly complicated techniques and get rid of bug sources. So that's sort of, this is my view of the Holy Grail. I want type and resource safe C++. And basically no leaks, no memory corruption, no garbage collector, basically because I don't want any garbage. And no limitations of expressibility. I can give you the first 3 very, very easy. I just stop you from doing anything interesting. It still has to be, it has to be able to do more than I can imagine, the usual criteria. Oh yeah, and it has to run as fast as usual, because otherwise people are not going to use this. You know, if you can't say what you want to say, or if it's too expensive to execute, people will do something else. So that is necessary, and I do not want to write another programming language. It's really hard work and it takes forever. So it has to be ISO C++, and I want tool enforced. This eventually shows it's there because, yeah, it's not perfect yet, it's work in progress, but we're getting there. There's an open source project for writing the guidelines. There's a little library that is supporting it. That's the library part of the drug cocktail. Most of that is a standard library, and a little bit is what's called GSL, the Guideline Support Library. We're trying to put that out of business by getting the things using GSL as a test bed, and the things that seems to be working and really good, we're moving into the standard library. So you're going to get our abstraction mechanism for sequences of elements in memory called a span, instead of having pointer and size, which you can get wrong. And we're trying to put our pre and post condition stuff out of business by getting contracts into the language. So basically, we want to put this one out of business, but you can download it and use it. It's portable, tested on GCC, Microsoft, and Clang. One of the interesting things here is the group of people that are involved in this. The people are typically in the meeting, in the phone meeting every week. Microsoft, Facebook, Morgan Stanley, Red Hat, and others. Notice Microsoft and Red Hat in regular consultation, and all of this is open source. So we're making progress. That's why I'll go for the Holy Grail. I'm not going to go details. Basically, you need an intellectual framework for the guides of what is good code. Because again, like a language feature, you can't evaluate in isolation. A rule for using a language feature, you cannot use in isolation. You need to have some philosophical backing for what you do, an intellectual framework. So that's what the philosopher is thinking here. We're doing this. We're writing standard C++, express ideas directly. Don't waste time and space. Don't leak. This is C++, right? So that's what we have. We want C++ on steroids, not some neutered subset. And so lower level rules sort of get you winding through the forest of problems. And so they can be mechanically checked. And so things like a single pointer points to a single object. If you want to refer to a sequence of objects, you better say so. One of the problems in C++ is you get a pointer. So, should you delete it? You don't know. Does it point to more than one element? You don't know. And so we have to unravel that mystery, and we do. There's abstraction called a span for doing much, and there's an abstraction called owner for dealing with ownership. Prefer initialization to assignment constructors, always initialize an object. These are relatively low level, simple to check statically rules. So if this all worked, I could give it to freshmen, and they would now write code that looked very much more like an expert's code than a freshman's code. Of course, they still wouldn't know their data structures and algorithms. This is not going to solve that level of problem. It's going to solve the problem of how you express your ideas, not whether you have any ideas. I mean, people have to remember a language is a tool. But yeah. And so basically, we want to get rid of my nightmare. That's a picture of a nightmare. If I delete something, I don't know if it's owner, so it looks innocent enough. But I don't really know whether that's something that's over on the free store. It may point to a local variable, in which case that'll crash the program. Here, I make a new, I call this one, I do something else and I use it. That can scramble the memory. This is really, really bad. So what went wrong there? Well, first of all, this won't be caught by the static checker because I'm deleting something that I don't know is on the free store. It will actually can catch this one. By the time you do this, it knows that you must delete this one and you've thrown away the information. So at least somewhere here, like there, it will give you an error. This is not the compiler. The language says this is perfectly all right till you get to there. But a static analyzer can say this is dangerous. We can deal with it. And the work going on here is to stop false positives. We shouldn't warn you more than is necessary. So that's fine. There's a set of rules that you can find actually in KNR for C. Dennis wrote most of the rules for lifetime. It's just we have not known how to enforce them. We're getting better. And then we have other things. If you overuse unions, we have variants. Don't use casts. Use an abstraction in the GSL to indicate whether a pointer can be null or not. If the pointer can't be null, you can run faster because you get rid of all of those tests. So performance has something to do with this, and so has correctness. Basically, this is a monster, and we want to deprive it of its habitat. And I think this monster is sort of more easy to deal with than that monster, because most of the time I can at least see that one. And we know it's easy to test for. And this is not science fiction. Here's a printout from Visual Studio from actually 2 years ago. Here I have the problem. I make a data structure, S42. This is some test code I wrote. And I sent it a pointer and another pointer. There's a structure, pointer, other pointer. The compiler, the static analyzer screams because I threw away the information that the one was on the free store. And therefore, that is a leak waiting to happen. And this is a fairly realistic leak. I mean, take this little stuff and put it in a million-line program and you're not going to spot it. We're not good at spotting things in million-line programs. Static analyzers are, provided they are local static analyzers, because if they were global and doing an n-cube algorithm, it doesn't scale. So you can write papers about it, but you can't deploy it. This is being tested out at Microsoft at million-line programs with a lot of pointers in them. So it's getting better. And if you have Visual Studio, you can just use it. It's the condition for me working with them is that it's all open source. So you can get it today. So there's lots of challenges. I mean, this is, as I said, this is not a perfect language or perfect solution to anything. It's pretty good at some things. We can do much better, and we must. Our civilization depends on software. Just imagine that software didn't work. So what wouldn't work? Well, your phone for starters, the lighting system here, your car, the transport system that brings your food in, your electricity would go out of business. You couldn't fly anywhere. There's C++ and all of that and other languages. So I'm taking this quite serious, and it has to be done on an industrial scale. We have billions of lines of code. We have at least 4.5 million developers. So everything has to be done gradually. One of the constraints of approving a language is that the feature has to be something that you can do gradually in a large program, otherwise it won't be used. It doesn't matter if I have the perfect solution if you have to throw away all your code to use it. Tough. It's hard. So basically, I think C++ is true to its principles, and those principles has been articulated for decades, even if people haven't listened. They're not new, and we make major progress over the years. We have to use what we have better. That's why the guidelines come in, and you can experiment with all of this today. I mean, you can try contracts, you can try concepts, you can try modules. It's all shipping in various places. And basically support us. We need support. Okay, so that was it. I'm a bit over time, but not much. So we have plenty of time for questions.
Any questions?
First of all, thank you very much for being here, Björn. I think all of us here are pretty excited to have you here, and thank you very much for the university to bring you here. And you clearly stated that your most favorite feature is probably the closing brackets.
Yeah?
Yeah, before. So I was going to ask you the other way around. If you had the power to change one single feature from the language or from the ecosystem, I don't care, what would you change?
The time machine question. If I had a time machine. Honestly, I don't know. And the reason for that is that if I remove anything major today without the time machine, then I will find that some small group of C++ programmers happen to depend on it, like 100,000 people. So I can't do it if it's major. If it's minor, it's a waste of time because it's minor. So I can't do that. I think basically the major features I like, and I don't know any major feature I couldn't improve quite a bit, but I think the bits and pieces that are there should be there. I definitely classes with constructors and destructors, definitely class hierarchies, definitely exceptions, definitely templates, definitely concepts, definitely modules. The major bits, I think, are the right major bits. And if you can't improve one of them in the abstract, if you didn't have the compatibility constraints, then you lack imagination. We know more than when they were put in place. And I'll give you an idea how hard it is to get something out. Have you heard about trigraphs? So if you have a keyboard, I think you all have a keyboard that has funny characters on them so that they have removed the square brackets and the backslash and things like that. That's true for Spanish, I believe. It's definitely true for Danish. We tried to get rid of the notation for handling that, which was something like question mark, slash for backslash and things like that. Gives really ugly code. Nobody was using it. And we tried to get rid of it. Turned out that the program that is the bootloader at the lowest level of every IBM system uses a trigraph as its first character. So by banning that, we would have killed every single system shipped by IBM or people collaborating with IBM. The howls from IBM were rather loud. And so it took another 3 years before we could basically make it optional to support trigraphs and allow them to do some slight subset of this so that they could still boot their systems. So this idea of stability is a very important one. That's why I called it the time machine question. Could I go back in time and fix it? And most of the things I would fix, I probably wouldn't matter. I mean, I really hate the declarative syntax of C. People love it once they've learned it, because now they feel clever. But it's really a mistake. Having a type notation that's not linear is just dumb. But Dennis had really good reasons for doing it that way. It had something to do with what parser technologies was available and the fact that he only had 48K to fit his compiler into. And once we had it, couldn't get rid of it again. The other thing is that everybody knows that conversions should not be value destroying and narrowing conversions, and they should be a lattice. And the C conversions are both ways. That creates havoc in any reasonable type system. So I would need a time machine, not just to get back and tell Bjarne something in 79. I needed a time machine to go back and tell Dennis in 72. And I would have to convince Dennis, under the constraint that he was working in the world that looked like in 72. And that is my sort of main problem with the time machine question, is that, Dennis knew more about computers and their users in 72. And vintage 79 Bjarne knows more about that world than I do, because I've forgotten a lot. I know much more about the current, his future, but it's really hard to mess with.
I really thought that you were going to say macros, but it's fine.
Again, if I had the time machine, I would definitely want to get rid of macros. There was a slide saying it. But once something is in the place, it's really hard to get rid of because people are using it. And the only way I know of getting rid of something in wide use is to provide something significantly better and then hope it withers rather than banning it. And maybe eventually we can get rid of it. I mean, the reason the macros are so awful is not the usual reasons. It's the fact that they spoil our IDEs. Because what you see is different from what the compiler sees, which makes it really hard to build interactive tools and better programming environment. So I'd love to do that. Modules is probably the biggest step in that direction. But I've been here before. I mean, people used to write for all macros. You have range 4s. People used to write funny macros to compute things at compile time. You have const expo. People used to write macros to generate particular data types. We have templates and template metaprogramming, and we have the templates for generic programming that again eliminates it. So basically my strategy there is to look at what is the most important thing people use macros for and then get rid of it. The problem is that people then start using macros for version control, and that I can't deal with. Then we had to get into build systems and how do you handle different ages of the language, and they do far too many macros for that.
Thank you for the amazing talk. My question is in the line of the macros. So, do you think that new proposals based on reflection idioms are going to be standardized soon, in order that we can do some string manipulations at compile time?
We are going to get almost certainly static reflection, and so let me just explain. There's languages that has dynamic reflection, which is basically have the compiler lay down a graph representing the program so that you can walk it and do things based on it. The snag about that is that if you do it, you escape all the rules of good programming by walking a data structure instead of relying on something with a well-defined semantics. And secondly, your programs bloat. We did some experiments. Programs tend to have sort of 80% 80% code, 20% data. And if you have reflection, it becomes 80% data and 20% code, and the amount of code is the same as it always was. So bloat. Ouch. Yes, this is real measurements. Not published because it was done by somebody commercial. Like they don't write these papers. That's one of the problems with C++ being an industrial language rather than an academic language. That is, I can have seen results, but they've never bothered to publish, and I can't even tell you exactly what it was because they don't want to tell. That's not academia, but that's the way it is. But we would still like to have some of the facilities for reflection. It would be really nice if I could say, here's a data structure. Give me an output operator and an input operator for this data structure, or give me a JSON writer and a JSON reader for that. This is the kind of stuff that if you have it as a graph, you can generate the code, or you can walk the graph doing the work. So we're going to get a version of something that does static reflection, which basically says, give me the JSON of X, or give me the stdio of X. And there is about 6 use cases I consider important. And I wrote a paper to the committee about it a couple of years ago. And there is, there are one or more proposals coming on. There's something called the reflection TS, which is all wrong. Everything in it is going to be removed because that was built on template metaprogramming, and the new thing, all the new stuff for metaprogramming, like Boost HANA and anything done in the last sort of 3 or 4 years is based on constexpr, compile time functions, which is much, much easier on the compiler and I think more logical, but it's going to go that way. Now, exactly what it'll look like, I don't know. There's still people writing papers about it. I'm sure there'll be new papers for Kona, but it's scheduled for C++ 23, and we will not know the details about what it is till then. But basically, it is a way of writing a little piece of code, metacode, that walks the data structures that the compiler has about your program. So that you can write code that says, if this class has a member called M, do this. And go through all the data members of this function and do something to each of them. So you can write a function for it and such. That's what it's going to be. Don't trust the details currently. They're changing.
More questions?
I would like to ask a question about something I read in some forums about some people think that maybe the C++ could be replaced by other languages, like, for example, Raj, or maybe even disappear in the future. What do you think about it? Thank you.
First of all, everybody was sure C++ wouldn't succeed in the first place. The fights in the early days was whether the language of the future was Smalltalk, Lisp, Ada, or Modular. After all, each of those were backed by powerful organizations and had commercial backing and lots of people involved. So I don't worry too much about this. I'm just trying to make C++ the best language it can be, given the constraints on the language design. Like, it's not trying to compete with, say, Python, or for anybody else that's totally dynamic. I don't like totally dynamic code. Where it's appropriate, it's not my business. So there's some principles there. And so it's, as far as I can see it, every language designed for reliability and performance, which are C++'s areas, over the last 30 years have had among its main goals to put C++ out of business. If I started worrying about that, I'd go crazy. And I would certainly go ineffective in improving C++. So I'm trying to learn, I'm trying to make C++ better. If somebody comes up with something that's better, good luck to it, it should win, if it really is better. Most of the time people come and say, look, this is simpler than C++, you should use it. Like the original Java ads showed people ripping out papers of the ARM about all of this stuff you didn't need. And at the time I said, well, if Java survives, it'll grow by at least a factor of 3 and it'll be much better for it. It did. So I don't believe in the simplicity argument, because by and large simplicity means you have either restricted domain, which is fine unless you claim to compete with C++. You can build more specialized languages better, shorter, even more efficient than C++ if you can narrow the domain. And then you'll probably implement it in C++. It could be that you're using LLVM to implement it, which also is C++. And so it's good to have many languages, and Rust in particular I like because it's following some of the principles of C++. It's got RAII. The thing that really annoys me is when I'm accused for having copied Rust in the areas that I was 30 years ahead of them. But that's fine. It's good that there's many languages, and C++ has a domain. It's not for everything and for everybody. That domain is huge and growing. There's about 4.5 million C++ programmers out there, and it seems to be growing by about 100,000 a year. What other languages are growing by 100,000 developers a year? Yeah, there are some, like JavaScript, but it's not in the same business. Also, I have sort of a policy not to be rude about C++ applications. And there we could mention, well, JavaScript and Java and C# and quite a few others. C++ is at the bottom of it a systems programming language that allows you to build systems with significant complexity. People keep falling into this trap of either you have to be low level or you have to be high level. With high level, you become inefficient and limited in the application area. Low level, you basically drown in your own complexity. C++'s unique place in the sort of programming universe is to do both systematically and deliberately. And if somebody can do that better, good luck to them.
Thank you, Professor. My question is related to garbage collection. Specifically, I know some libraries that have tried to implement garbage collection using reference counting. My question is, the choice of not including garbage collection in C++, is it because it's not optimal, or because it will be a lot of effort to include in the list, or both?
I mean, if I was going to implement a garbage collector, I wouldn't use use counting. I mean, there's languages that do that, but I wouldn't go that way. I'd start with a sweep and mark and then upgrade it to modern things. But the point is, I think fundamentally I don't like garbage. I started out with C++ doing things where garbage collection delays were unacceptable. It would give real time. If you write something that wiggles wingtips of planes or deals with voice manipulation of amplifiers and things like that, you just don't do that. You can't have a delay. Furthermore, the fact that you have a good garbage collector, it's usually copying, you need twice as much memory. I have lots and lots of people, friends, who build systems where twice as much memory they have good uses for. They don't want to give it to a garbage collector. Similarly, the garbage collector tends to introduce extra indirections in your code implicitly. So in the C++, you see a type T. If it goes and uses the free store, that's its job, and it'll show the semantics. But by default, you can put it on the stack, and it will work there. It's usually much faster than having it on the free store. So the language for supporting garbage collection is inherently inefficient because it has more indirections. And that was sort of the start of the game. I just couldn't afford it. And I thought for a while that maybe something would happen so I could afford it, but it never happens. So I'm getting harder and harder on this topic. I want to eliminate garbage. And if I eliminate garbage, I've eliminated the garbage collector because there's no need for it. I'll give you one fairly concrete example. A friend of mine was experimenting to try and figure out the benefits and weaknesses of Common Lisp compared to C++. And he wrote a nice program in both languages, and the Lisp guys were really quite pleased because the Lisp was only 3 times slower than C++, and as the computers were still running faster and faster every year, the argument was just wait 3 years and we'll run as fast as you do today. My argument would be in 3 years I'll still run 3 times faster than you. But enough is enough. I mean, if it's fast enough relative to your job, you can waste as much time as you want. I mean, there's lots of things where Python would be totally unsuitable, and there's lots of things where your computers are just fast enough to run that way, or Ruby or something. Now, what happened next is the interesting bit. He gave it some more data, and the Lisp started running 12 times as slow as C++, meaning it used 12 times as much time. And the garbage collector had cut in because it needed to, because they were running out of memory. And I said, okay, so it's 12 times as slow. And they said, it's unfair. We're preserving the memory. And I said, it's perfectly fair. I don't waste memory, so I didn't run out. And it's arguments like that that is an advantage to the C++ approach. The weakness of the C++ approach, to be fair, is that if you have an object and you have to manually manage the free store, you can have a pointer to something, you can have another pointer to it, you can delete the first one, and you can access it through the second one. That's memory corruption. In full C++, there's no way of avoiding that. If you use the static analyzer that I was doing and the guidelines, this cannot happen anymore. And so that's a very important aspect of distinguishing between the language and the use of the language. So I need to get rid of the garbage collector, that's good, but I also have to be able to get the benefits that you actually get from a garbage collector, which is the language that avoids memory corruption by basically keeping the types straight. And I can do it. But that was work in progress, so I can't actually, if you use Visual Studio and the static analyzer there, you can get it today. But some of us works in shops that are not Microsoft shops. So I wanted in all of the, I wanted that static analyzer applicable to any program. Once that happens, I can make a stronger answer.
Another question?
Thanks for the presentation, and I would like to know if there is any support for machine learning in C++.
There's no direct support for machine learning in C++. I suggest you use something like TensorFlow, which is a C++ program. It's essentially all C++, but in some sweet and sour sauce, right? That often is another language. But that is a typical job, it's a core job of C++, is to do the really hard parts on which everybody else can depend on.
Thank you very much for the presentation. I wanted to ask, out of the new languages that you see nowadays, which one maybe has inspired you for newer features in C++?
Interestingly enough, that's not the way it works. I look at other languages and sometimes I get an idea, but it is really hard to move a feature from another language in without mutating it. So it's more sort of distant inspiration than direct borrowing. And the thing that really drives me, at least, not necessarily the whole committee, I mean definitely not the whole committee, is looking at what problems do people actually have. What is it that makes developers miserable, and see if we can do something about it. And once I know what the problems are, I look around to see whether somebody else has solved this problem first. And then I can borrow from it, always with acknowledgements. And that could be research results, academic results, it could be some other language, but it's not looking around for things to borrow. It's the opposite way of doing it. You first figure out what the problem is, then you see if anybody else has the solution.
Okay, we take the last question. Probably you want to go for lunch, and we will be here again at 4 p.m.
Thank you for the presentation. You were talking about memory leaks, memory corruption, and what about memory fragmentation?
Fragmentation is a somewhat difficult problem, and so you probably know that if you write flight software, you're not allowed to use any form of free store because it might fragment. And so basically a lot of the rules are that you cannot use new after the engine is started, and you can never use delete. And so in that world, today, what you do is you provide a pool allocator and a stack allocator, and then you build libraries on top of that uses those rather than the general free store. Again, you can solve the fragmentation problem, but only if you can afford relocation. And the same kind of systems that can't afford the free store, the fragmentation, cannot afford the relocation. So you would have to put something in place where you are still under hard real-time constraints, and you have to be able to do movement. And if somebody figures that one out, they should be welcome, but I have stayed out of that domain. So if you can't use free store, if you must guarantee there's no fragmentation, go to pool allocators and stack allocators. They can't fragment. And I'm arguing for getting pools and stack allocation into the standard library, because the support for that kind of stuff is really poor now, because the majority of the committee doesn't understand these problems. It's not their world. They're used to a computer being a big monster with a screen. And most of the problems with fragmentation is not in those systems.
Okay, thank you very much. Thank you, Bjarne. So as I said, we will be here at 4 again with a much more detailed talk. So I hope to see you then. Thank you.